Good day everyone, I am GloryAnn Ytang from BSE 3B Mathematics. Our topic for today is all about Wilson's theorem. So let's go. For our objectives, at the end of this lesson, the students will be able to define and discuss Wilson's theorem, explain the basic facts about the theorem, and lastly, solve problems related to finding remainders using Wilson's theorem. But before we start, here's a quote according to Sun Tzu. There are certain things whose number is unknown. When divided by 3, the remainder is 2. When divided by 5, the remainder is 3. And when divided by 7, the remainder is 2. What will be the number of things? So Wilson's theorem. According to Wikipedia, in number theory, it states that a natural number n is greater than 1 is a prime number if and only if the product of all the positive integers less than n is 1 less than a multiple of n. That is, using the notations of modular arithmetic, one has that the factorial n minus 1 factorial is equal to 1 times 2 times 3 and so on. It satisfies that n minus 1 factorial is equal to negative 1 mod n. Do you know that the modulo or modulus or mod is the remainder after dividing one number by another? So, for you to understand Wilson's theorem, here's the example. Examples of finding remainders using Wilson's theorem. For the following questions, we will be frequently using Wilson's theorem, which states that for a prime p minus 1 factorial is identical to negative 1 mod p. So here's the example number 1. Find the remainder of 97 factorial when divided by 101. First, we will apply Wilson's theorem to note that 100 factorial is identical to negative 1 mod 101. When we decompose the factorial, we get that 100 times 99 times 98 times 97 factorial is identical to negative 1 mod 101. Now, we note that 100 is identical to negative 1 mod 101 and 99 is identical to negative 2 mod 101 and 98 is identical to negative 3 mod 101. Hence, negative 1 times negative 2 times negative 3 is equal to negative 6 and 97 factorial is equal to negative 1 mod 101. So, remove the negative signs and it is equal to 6 times the quantity of 97 factorial is identical to mod 101. Now, we want to find a modular inverse of 6 mod 101. Using the division algorithm, we get that 6 times 16 plus 5 is equal to 101. 5 times the quantity of 1 plus 1 is equal to 6, and 6 plus 5 times the quantity of negative 1 is equal to 1, and 6 plus 101 plus 6 times the quantity of negative 16 times the quantity of negative 1 is equal to 1. So, 101 times the quantity of negative 1 plus 6 times the quantity of 17 is equal to 1. Hence, 17 can be used as an inverse for 6 mod 101. It does follow that 17 times the quantity of 6 times 97 factorial is identical to 17 factorial mod 101. 97 factorial is equal to 17 mod 101. Hence, 97 factorial has remainder of 17 when divided by 101. For you to understand the topic, here's the example number 2. Find the remainder of 67 factorial when divided by 71. Using Wilson's theorem, we have that 70 factorial is identical to negative 1 mod 71. By composing the factorial, we get that 70 times 69 times 68 times 67 factorial is identical to negative 1 mod 71. Negative 1 times negative 2 times negative 3 is equal to negative 6 times 67 factorial is identical to negative 1 mod 71. So, remove the negative signs. It is equal to 6 times 67 factorial is identical to 1 mod 71. And now, let's find a modular inverse of 6 mod 71 by the division algorithm. 6 times 11 plus 5 is equal to 71. 5 times 1 plus 1 is equal to 6. 6 plus 5 times the quantity of negative 1 is 1. 6 plus 71 plus 6 times the quantity of negative 11 times the negative 1 is equal to 1. And 71 times the quantity of negative 1 plus 6 times the quantity of 12 is equal to 1. Hence, 12 can be used as an inverse. Thus, 12 times the quantity of 6 times 67 factorial is equal to 67 factorial. 12 times 1 is equal to 12 and mod 71. Hence, when 67 factorial is divided by 71, the remainder left over is 12. So that's all for this video. I hope you will learn a lot. Thank you for watching.